Hello everyone, this is Professor Roman. Let's continue the ring theory lectures. We are now ready to take a closer look at integral domains, of which there are many types. Principal ideal domains, we've already discussed briefly, unique factorization domains, and Euclidean domains. And we'll talk about each of these either in this chapter or the next. Let's begin with just a very quick review, so we're all on the same page, refresh our memories. If R is a commutative ring, a non-zero element, little r, in R is called a zero divisor if there is a non-zero S in R for which Rs equals 0. And a commutative ring with identity is called an integral domain if it contains no zero divisors. Here are some simple examples I'll let you take a look at. I've already discussed some of these. If m is an integer that's not a perfect square, then this set z plus z square root of m, so that's all the elements of the form a plus b square root of m where a and b are integers. This, of course, is a subset of the complex numbers. This is an integral domain under addition and multiplication of complex numbers. It's an example of what we call a quadratic integral domain because square root of m satisfies a quadratic polynomial over the integers. I think it's also called a quadratic domain, and I'm going to leave verification of this to you. Here's another quadratic domain. Let m be an integer that is not a perfect square, then this set is a ring under addition and multiplication of complex numbers if and only if m is congruent to 1 mod 4. And I'm going to let you verify that. When m is congruent to 1 mod 4, this is a quadratic integral domain. We'll have more to say about quadratic integral domains. They're very useful in finding, say, counterexamples of things. And they're important in number theory. Theorem, this, I believe we've discussed all of this before. A commutative ring R is an integral domain if and only if the cancellation law holds. Cancellation law is very important. We use it often, quite often. Integral domains are strongly associate. That means that two elements are mutual divisors if and only if they are associates, which by our definition means unit related. A finite integral domain is a field. An ideal I of a commutative ring R is prime if and only if the quotient ring R mod I is an integral domain. And finally, if R is an integral domain, and if A divides B, then there's a unique alpha for which B equals alpha A, and we can write it using these symbols. Now, let's take a look at prime and irreducible elements. As soon as I figure out how to get these pages separated. Here we go. Okay, now, if you ask people on the street what's a prime number, if they don't tell you to buzz off, they're likely to say it's an integer or a number greater than 1 that has no divisors other than 1 and itself. Well, that is in fact not the definition of prime element in an integral domain. There are in fact two types of indecomposable elements in an integral domain. And when those two types are equivalent, as they are in the integers, the two terms tend to get used interchangeably, even though they are distinct quite different concepts. So here's the definition. R is an integral domain. First of all, a factorization of an element little r into a product AB is called a trivial factorization if one of the factors is a unit. Otherwise, we'd say it's a non-trivial factorization. A non-zero, non-unit little r is said to be irreducible if it has no non-trivial factorizations. So another way to say that is its only factors are units and associates of itself. Otherwise, the element is said to be reducible. So reducible means it can be factored into a product of two elements, neither one of which is a unit, and therefore neither one of which is an associate of the element R. And so it's a real factorization. It's factorization into, this isn't the right word, but smaller factors. I wouldn't use that word, but it conveys an idea. A non-zero non-unit, P, is said to be prime if P divides a product AB, implies P divides one of the factors. Note carefully that both of these, irreducible and prime, they have to be non-zero non-units. If R is prime or irreducible, then so is any associate of R. Now, in the integers, it turns out, as we'll see, that these two concepts are equivalent, prime and irreducible, but they're still distinct concepts. And so if you're going to refer to the term prime as its real meaning in ring theory, then when you say an integer is prime, you have to say that's true if whenever it divides a product, it divides one or the other, not it has no non-trivial factors. To explore the relationship between these two concepts, we can first express them in terms of principal ideals. And subsequently we'll show that prime elements are always irreducible. But the converse is not true. So primeness is a stronger condition than irreducibility. Theorem, let R be an integral domain and let P be the family of all non-zero proper principal ideals of R. Then little r in R is irreducible if and only if the ideal it generates is maximal in this set, in this family, script P. P is prime if and only if the ideal it generates is a non-zero prime ideal in R. Okay. Be careful about this maximal ideal. It's maximal only in this family, P. Okay. Not necessarily in the family of all ideals. So it's not a maximal ideal in R. It's a maximal ideal in the family P. Any prime element is irreducible. The converse does not hold in general. If R is a principal ideal domain, then an element little r is prime if and only if it's irreducible. So that covers the case of the integers. For the proof of part 1, if R is irreducible and the ideal generated by R is contained in an ideal generated by S, which is proper, then R is some multiple of S, say R equals AS, and since S is not a unit because this is proper, A must be a unit. And so R and S are in fact associates, and these two ideals are equal. So that means that the ideal generated by R is maximal among the proper principal ideals. Conversely, if this ideal generated by R is maximal in that family, and if R can be factored as a product AB, then R belongs to the ideal generated by A, and so the ideal generated by R is contained in the ideal generated by A. But this is maximal, and so the ideal generated by A must be either equal to the ideal generated by R or must be all of the integral domain. In the latter case, A is a unit. In the former case, A and R are associates. And so R is a unit times A, but it's also equal to AB, and so B is a unit. And thus R is irreducible. For part 2, a non-zero ideal generated by an element P is prime if and only if P is a non-zero, non-unit. Remember, prime ideals by definition have to be proper, so that's why it has to be a non-unit. Okay. And this is the definition of primeness for an ideal, a non-zero proper ideal. But that is exactly the same as this statement, which is the definition of primeness. For part 3, let me refresh our memory here on that one. Any prime element of R is irreducible. The converse does not hold in general. So let P be prime and suppose it factors as a product AB. Then, of course, P divides AB, divides itself. And we can assume by symmetry here that P divides A, in which case A is XP, which is XAB. X is just an element of the ring, so we cancel the A's and we get 1 equals XB. B is a unit. Okay. So P is irreducible. We're going to do an example in a minute to show that the converse does not hold. Finally, for part 4, which is that in a principal ideal domain, an element is prime if and only if it's irreducible, we just need to show that irreducible elements are prime. If R is irreducible, then this ideal generated by R is maximal and non-zero in the family P, and therefore it is prime and non-zero. So I'm going to let you fill in the reason for the therefore here. So R is prime. Here is an example to support the fact that irreducible elements need not be prime. And this is a quadratic domain, z plus z square root of negative 5. Now, as with the Gaussian integers we talked about before, we can define the quadratic norm function. And it looks like this. The norm of a plus b squared of negative 5 is a squared plus 5b squared. It's the square of the usual complex norm. The norm is multiplicative. An element is 0 if and only if its norm is 0. And the norm of an element is 1 if and only if x is plus or minus 1. I should say positive or negative 1, and you can check that. So if a product xy equals 0, then taking norms gives norm of x, norm of y is 0. And so one of these norms has to be 0, which means one of the elements has to be 0. And there are no 0 divisors. So this is, in fact, an integral domain. The units in R can be computed as follows. For x and y in the ring, xy equals 1 implies the norm of xy equals 1. which implies x, y is positive or negative 1, and so x and y belong to this set. These are both units, and so those are the units. We can also test for irreducibility using the norm function. Here are four elements that are irreducible in fact. For example, oops, I got this twice, I'll have to fix that. To see that 3 is irreducible, we write 3 equals xy and take norms. Norm of x, norm of y is then equal to the norm of 3, which is 3 squared. Remember, these are integers. This is one of the great virtues of the norm. We pass from an arbitrary integral domain, or quadratic domain, to the integers, where things are much more pleasant. How can the product of two integers be equal to 3 squared? Well, one possibility is that one of these has, these factors are both equal to 3, but there is no element of this ring that has norm 3. You can check that easily. So one of x or y must have norm 1, the other has norm 9, and so the one that has norm 1 is a unit. Similar argument, say, for this element. If this is a product of x, y, we take norms again, and the norm of this is 1 squared plus 2 squared times 5. So it's 1 plus 4 times 5 is 20. It's 21, which is 3 times 7. Again, neither of these can have norm 3. So one of them has norm 1, the other has norm 21, and so we have a unit. And the other two, the proof is quite similar. Okay. Note also that none of these 4 elements are associates. And I'll let you work out a detailed reason for that based on the fact that they're irreducible and we know what the units look like. Something worth thinking about. Now, the irreducible element 3 is not prime. Excuse me. And the reason is that the product of this element 1 plus 2 square root of 5 and 1 minus 2 square root of 5, negative 5 is 7 times 3. So 3 divides this product. But 3 will not divide either factor. For example, if 3 were to divide 1 plus 2 squared of negative 5, then we'd have an equation that looked like this. 1 plus 2 square root of negative 5 equals a plus b, square root negative 5 times 3. No integral solutions. Remember, a and b have to be integers. Okay. 3 doesn't divide the other factor either, and the argument is similar. So 3 is not prime. It divides a product, this product, but it doesn't divide either factor. Okay. Now there's something also very important going on here in this factorization, because 3 does divide this product, obviously, and it doesn't divide this product, but these products are the same value when you actually take the product. So this is a tip-off that weird things can go on in integral domains that are not nice. They don't have any additional properties that we'll discuss later. In this case, unique factorization into irreducibles. That causes a lot of problems. if that property is missing. So we in fact have an element here, 21, that is factorable in two distinct ways into a product of irreducible elements. Okay? And we'll return to this issue as we go on. Okay, so it's important to get the mindset here now. We're not dealing with integers anymore. This is kind of reminds me of the Wizard of Oz. This is not Kansas. Okay, life is going to be a little more unusual, and it's important not to jump to any unwarranted conclusions because we're so familiar with the integers, which is not only a principal ideal domain, but a unique factorization domain, and so that life is much more well-behaved there. Okay, next we come to an example of an integral domain that has no irreducible elements whatsoever, and therefore no prime elements, because prime elements are irreducible. Now the key observation in this example is that non-constant complex, what I'm just calling pseudo-polynomials, in other words, polynomials with non-negative rational exponents. So here's an example. 1 plus 2x to the 1/2 plus 3x to the 2/3. They can always be factored in a non-trivial way. Here's how you would do it with this polynomial. F of x to the 6th is an ordinary polynomial, clears all the denominators and the exponents, and it's non-constant because this was non-constant, and so it has a complex root, r. So f of x to the 6th has a factor x minus r. We get this for some quadratic polynomial. This is cubic. P of x is quadratic, so it's non-constant. Then we pass back, drop the x to the 6th. F of x looks like this. That is a non-trivial factorization of f of x. So f of x is not irreducible, it's reducible. Same argument works in general. With an expression like this, we can assume that the exponents are distinct, and we proceed, addition and multiplication is just the ordinary rules of algebra, and the units of this set are the non-zero complex numbers. This is in fact a ring. And so what we can do, and it's an integral domain, we can show that no element is irreducible. And I do exactly the same thing as before. If n is 1, then we just have a single term. And if r over s is 0, then we get a unit. If r over s is not 0, the exponent's not 0, then we can just factor this way, showing that f is not irreducible. If n is bigger than 1, we have something that looks like this. Find the least common multiple of the denominators in the exponents. Do exactly what we did in the example. Here's the linear factor. We get this factorization. Okay. So this is just a little bit of algebra. So we have an integral domain with no irreducible or prime elements at all. Now we're going to start our study of divisibility in integral domains. And this is going to be a little testy. There's some unusual behavior. We've already noticed that in a previous example, because we cannot rely on unique factorization, we can't say that every element, a non-zero, non-unit, can be factored as a product of irreducible elements. Life is complicated. So we'll try to go through this as slowly and carefully as we can. The first part is just a warm-up. We have seen that divisibility is more well-behaved in integral domains than it is in arbitrary commutative rings. In particular, integral domains are strongly associate. That makes life much simpler. The relation of being associate is easily seen to be an equivalence relation, and I'll leave that for you, and the equivalence classes are known as associate classes. So, in short, two elements are in the same associate class if and only if they're associates. In the ring Z of integers, the units are plus and minus, positive and negative 1. So the associate classes are sets that contain two elements, positive and negative A. The Gaussian integers, the units are positive and negative 1, positive and negative I. So the associate classes have four elements. They look like this. I think we've discussed this before. I believe we've had this before, but I don't remember, and I'll leave the proof for you. This is divisibility framed completely in terms of principal ideals. In an integral domain, U is a unit if and only if it generates the entire ring. R divides S if and only if the ideal generated by S is contained in the ideal generated by R. R and S are associates if and only if the ideals they generate are equal. And R properly divides S if and only if the ideal generated by S is properly contained in the ideal generated by R. Let us now turn our attention to the subject of common divisors and greatest common divisors, and also common multiples and least common multiples in an integral domain. In an integral domain R, every finite set of elements has at least one common divisor, namely the identity, or in fact any unit. And it also has at least one common multiple, namely the product of the elements. And here is the official definition. R is an integral domain. A is a non-empty finite subset of R. A common divisor of the set A, or of its elements, is an element D in R that divides all the elements in the set A. And I'll use this notation for the set of common divisors of A, or of the set A1 through AN. Similarly, a common multiple of A is an element C in R that is a multiple of every element in the set A. And I'll use these notations, Cm of A, or Cm of A1 through AN, for the set of common multiples. This is a notation that we will have some use for. This stands for the set of all common multiples of A1 through AN that divide the product. If D is a common divisor of the set A, then so is any associate of D, or put another way, CD of A is a union of associate classes. And a similar statement will hold for Cm. You can say in yet another way, CD of A is closed under associate, and is therefore a union of associate classes. the non-zero elements A1 through AN are relatively prime if they have no non-unit common divisors, or in other words, if CD of A is the set of units. The units are always common divisors. As you know, experience with the positive integers, which by the way is not a ring, but does tell us, generally speaking, that it's the unique greatest common divisor and the unique least common multiple that are the most interesting and the most useful. Unfortunately, however, these objects do not always exist in arbitrary integral domains. And even when they do, they are not, in general, unique. Here's the definitions. R is an integral domain. Again, A is a non-empty finite subset. A greatest common divisor, or GCD, of A is a common divisor D with the property that if E is also a common divisor of A, then E divides D. In other words, D is greatest in the set of divisors of A under divisibility. Now, the term greatest is slightly misleading. We generally reserve a term like that, at least in the context of partially ordered sets, for the largest element, the greatest element, and it is unique. But here, we don't have a partially ordered set because we don't have symmetry. Divisibility doesn't give us symmetry in this case, only, you might say, symmetry up to unit. So the term greatest, so as a result, there can be, and often is, more than one greatest element, more than one greatest common divisor, more than one least common multiple. A least common multiple of A is a common multiple of A, call it M, with the property that if E is also a common multiple of A, then M divides E. We'll use the usual notation, GCD of A and LCM of A, for these two sets. We're also going to have use for these two terms. An integral domain in which every two elements have a greatest common divisor is called a GCD domain. And similarly, an integral domain in which every two elements have a least common multiple is called an LCM domain. For the positive integers, least common multiples and greatest common divisors are unique, but even in the full ring of integers, that fails. And greatest common divisors and least common multiples are unique only up to associate, and in the integers that means up to algebraic sign. These sets, GCD of A and LCM of A, when they are non-empty, are associate classes. It's not difficult to see that GCD of A is closed under associate, so it's a union of associate classes. But if D and E are greatest common divisors of A, that means they divide each other. So they are mutual divisors, and in an integral domain, then, therefore, they are associates, and so they belong to the same associate class. So GCD of A is either empty or it's an associate class. And similarly for LCM of A. Put another way, greatest common divisors and unique and least common multiples are unique up to associate. Example, the ring of integers, the GCD of 12 and 21 is 3 and negative 3. The LCM is 84 and negative 84. These two are associate classes. Let's take a look now at some properties of the sets of common divisors and common multiples, CD of A and CM of A. Suppose first that little r is an element of the integral domain and A is non-empty finite subset. Then what can we say about the set CD of R times A? Well, any product of the form D times E where D divides R and C is a common divisor of A will be a common divisor of RA. I'll say it again, this is something that should be pretty obvious. If D divides R and E divides all the elements of A, then the product DE divides all the elements of RA. And so div R times CD of A is contained in CD of RA. But it turns out that this inclusion is sometimes, oftentimes, proper. Other times it's an equality. In the case of the integers, for example, if x is a common divisor of RA, then we can write the following. And I'm going to, in this case, CD of XR, let's just pretend that's a fixed common divisor, a greatest common divisor. There's only two of them, they're positive and negative. So let's just take the positive greatest common divisor. Okay. So we can write x as that positive greatest common divisor times x over that divisor and call that ED. This is E and this is D. Well, E divides R. It's a greatest common divisor of X and R, therefore it divides R. D, on the other hand, is relatively prime to R. Therefore, since D is a common divisor of RA, but D and R are relatively prime, D must be a common divisor of A. And so X, which is ED, belongs to this set. So that's the reverse inclusion, and we have equality. But again, this does not hold in all integral domains. The integers are very special. The reason this is working out is not just for the integers, but for any integral domain in which you can uniquely factor elements into products of irreducible elements, unique up to order and up to associate. We're going to talk about that concept in the next chapter. Okay, but for now, it's just important to realize that this expression is oftentimes proper inclusion. Other times it's equality in more well-behaved integral domains. What can happen in less well-behaved integral domains is that multiplying the elements of a set A by a single element R can actually produce additional common divisors of RA that are not of this form. They're not a divisor of R times a common divisor of A. And I'm going to show you an example of that now. In this quadratic domain, z plus z squared of negative 3, the three elements, 2 and alpha equals 1 plus square root negative 3, beta equals 1 minus square root negative 3. These are irreducible and they're non-associates. It's quite clear they're non-associates because the only two units in this quadratic domain, as it was for a different quadratic domain we discussed earlier, are positive and negative 1, and none of these are negatives of the other. As to their irreducibility, we can actually prove that for all three at the same time. So let's say delta represents any of these elements. And suppose delta has a factorization that looks like this. Then we need to show one of the factors is a unit. Taking quadratic norms, each of these has norm 4. That's why this single argument works for all three of these. Okay. So we get 4 equals, norm here is a squared plus 3b squared, c squared plus 3d squared. Write it all out. There's a 9 here. All the other terms are non-negative, so b squared, d squared has to be 0. We're in an integral domain, so bd has to be 0, and one of b or d has to be 0. And there's a symmetry here in these two factors, so we can assume that d is equal to 0. If b is also 0, this one, then this reads delta equals ac. Remember, a and c have to be integers. The only time this can hold is if delta is in fact 2, and then the factorization is trivial. One of the factors is a unit. If b is not 0, then we knock out the terms that have d in them because they're 0. We're left with this. But because we have non-negative terms everywhere, this is bigger than or equal to 3c squared. And since that's equal to 4, c has to be either positive or negative 1. And then c plus d squared of negative 3, this second factor here, is a unit. It's positive or negative 1. So no matter how you try to factor this, one of the factors is positive or negative 1, is a unit, and so delta is irreducible. This also means, since they're non-associates, that any two of these three are relatively prime. Now, since alpha and beta are irreducible non-associates, the set of greatest common divisors of alpha beta is the set of units, which in this case consists of just the numbers positive and negative 1. Now let's multiply these two elements, alpha and beta, by alpha. Alpha squared is equal to negative 2 plus 2 square root negative 3. Alpha beta is equal to this product, which is 4. And so now let's compute the common divisors of these two elements, alpha squared and alpha beta. The first step, one approach anyway, is to find the divisors of alpha beta, which is 4. So we write this equation, and we can assume that a is non-negative because for factorizations where it's negative, we can move the negative sign to the other factor. So this doesn't lose any generality. Taking quadratic norms gives this, and symmetry now allows us to restrict attention to the cases where this factor is either 1, 2, or 4. For example, if this factor was 8, then the other factor would be 2, so we would be covering that case if we just restrict attention to these three possibilities. Another way to say that is we can assume one of the factors is 1, 2, or 4, and it doesn't matter which one, so it may as well be this one. Well, if a squared plus 3b squared is equal to 1, then a is 1, b is 0, and our factorization here is just the trivial factorization. 4 equals 1 times 4. The case a squared plus 3b squared equals 2 is not possible within the integers. For the third possibility, a squared plus 3b squared equals 4, we have either a equals 2, b equals 0, or a equals 1, b equals positive or negative 1. For the case a equals 2, b equals 0, then we now have a equals 2, d is 0, and so c plus d square root negative 3 has to be 2. And therefore c has to be 2 and d has to be 0. So that gives the factorization 4 equals 2 times 2. I think I said d was 0 before. I didn't mean to say that. D is 0 because of this. The final possibility is a equals 1, b equals positive or negative 1. Then this is a, b is positive or negative 1. This is the other factor. That's equal to 4. But 4 can be factored this way. And whichever sign you take, this factor will cancel with one or the other of these, leaving c plus d square root negative 3 to be the other factor. So the only factorization we get here is this one. So we've exhausted the possibilities, and we can collect the divisors of 4. 1, 2, 4, and 1 plus or minus square root negative 3, and then the associates of those, so that's why there's a plus and minus sign here. Now we need to examine these divisors for divisors of alpha squared. That will give us the common divisors. Certainly 1, 2, and 1 minus square root negative 3 divide alpha squared, so they are common divisors. There's two other elements here to check. If 2 divides alpha squared, there's alpha squared, then, if 4 divides alpha squared, then 2 must divide 1 minus square root negative 3, but that's irreducible. 2 is not a unit, so that can't happen. So 4 is out. It's not a common divisor. But alpha squared, which is this value, can be written this way. And so, excuse me, getting over a cold. And so 1 plus square root negative 3 is a factor of alpha squared. So the common factors of alpha squared and alpha beta are these elements, which is the same as the common of the divisors of alpha beta except for 4. Now we can gather everything together. The divisors of alpha are these two and their negatives because alpha is irreducible. Common divisors of alpha and beta are positive and negative 1. Common divisors of alpha squared and alpha beta are here. That's what we just finished doing. So div alpha times common divisors of alpha beta is this set, but common divisors of alpha squared alpha beta is this set, which contains positive and negative 2. So the inclusion here is proper. What happened is, I mentioned before, when we multiplied alpha and beta by an element, in this case alpha, we actually discovered a new, in this case, 2 divisors, positive and negative 2, that were not of this form. Divisor of alpha times common divisor of alpha beta. Okay, there's one other thing to note here that we will refer to in a few minutes, and that is that while the greatest common divisors of alpha and beta are the units, so they exist, the elements alpha squared and alpha beta do not have a greatest common divisor. Of course, if there were a greatest common divisor, it would have to come from the set of common divisors, which is this set here. If one of these is greatest, then the others divide it. So 1 is ruled out immediately, but 2 and 1 plus or minus square root negative 3 are irreducible, and these are non-associates, so there cannot be a greatest element in here. So the situation we have is that the GCD of alpha and beta is non-empty, consists of positive and negative 1, but when we multiply alpha and beta by alpha, there are no GCDs. Strange behavior, because essentially of the lack of unique factorization into irreducible elements. A subject, again, we'll take up in the next chapter. So this equation, then, which seems like it should be reasonable, does not necessarily hold. And we'll talk about that in a minute. Let's examine now common multiples. It is not difficult to see that if M is a common multiple of A, then Rm is a common multiple of Ra, and conversely. This requires cancellation and therefore an integral domain. So R times the common multiples of A is contained in the common multiples of Ra. But the story is different here. It's nicer. This is always an equality, because if n is a common multiple of Ra, I guess first we should say, I didn't say this, if there are no common multiples of Ra, this is empty, then this side is also empty, so they're equal. But otherwise, if n is a common multiple of Ra, then for each little a in A, there is an element, which I'll call alpha sub A, because it depends on A, little a, for which n equals alpha A Ra. N is a multiple of Ra. So R divides n. N over R is alpha A, and that's for all little a in capital A. And so n over R is a common multiple of A, and we can write n in the form R times n over R, which is in the set R times the common multiples of A. So this is equality. Summarize. R is an integral domain. A is a subset of R, non-empty and finite. Little r belongs to R. Then the best we can do for common divisors is this inequality, set inclusion, which in fact can be proper. But for common multiples, we have a nice formula here, always, even though both of these may be empty.